record to this computer. Okay, screen being shared, my voice is being recorded. Good. Okay, so we can start today's lecture. Okay. So first of all, I hope you enjoy your Chinese New Year holiday. Okay, and you have a great refreshment or you within the Chinese New Year holiday. And now we will need to resume with our regular class schedules. Okay. And one thing, okay, I will need to talk about is the arrangement of the assignment one. Okay. I've already finished the design of the assignment one. Okay, but I still want to go through the assignment ones to make sure that it's no mistakes. Okay, it's not a fun thing. If I suddenly send you an email and tell you that there is something that the assignment one is wrong and you just need to update it. Okay. So for the assignment one, okay, I will release it on Wednesday. Okay. If everything goes well, I will release it on Wednesday. And when I release it on Wednesday, I will send you an email. I will send you a mass email to notify you as well. Okay. The assignment will be released to the Moodle platform. Okay. Okay. And just in case, okay. Just in case you don't know, okay, the assignment will be a written assignment. And in fact, in this course, all the assignment will be written assignment except the project. Okay. The main rationale behind the written assignment arrangement is that you should already master how to write program, how to write program. You should already master all the basic techniques of writing programs in your programming course. So this course is about algorithm, okay, and I would not examine your programming abilities in this course. So all the assignments will be written assignment and will be designed to examine your understanding on the algorithms. Okay, but talking about algorithm without source code, without the actual coding implementation is difficult. So this is the reason why I also included reference coding in the Moodle for your reference. I believe that some students they don't like to read a lot of text, a lot of dull text in the lecture notes, okay? But they can master the algorithm better by looking at the source code. Okay, so I also give you that option as well. Okay, but in reality, when we are talking the understanding of the algorithm, okay, the programming coding part is not a must. Okay, in fact, in many universities, okay, they taught algorithms with pseudocode. Okay, because at the end of the day, when you are teaching algorithm, it can be as abstract as talking about mathematics. But here we are taking a approach that it is in the middle. Okay, we also cover some implementation and we also cover some algorithm discussion part. Okay, so any question regarding the arrangement of the assignment one? It will be a written assignment. I will release it on Wednesday, and I will send you an email just to make sure everyone get the message. Okay, and don't worry, it will not be difficult. It is just doing the things we have been talking about in the lectures. Okay, and so let's go through the lectures. Why is not? Maybe I will use. Okay, it works anyway. Wait. So last time in the last lecture, if my memory serves correct, okay, we have go through the breadth search. Essentially, we actually go through the discussion on the complexity of the breadth search. okay? Or we do a conceptual discussion on that. And we also go through the uniform cause search, okay? Essentially, okay, the main differences of the breadth search and the uniform cause search is that we swap out the heap, we swap out the fringe, okay? Instead of using the queue as the fringe, we are using a priority queue. Okay? 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 And when we are talking priority queue, okay, when we are talking about priority queue, when we are talking priority queue is actually a data structure that behaves like this. Okay. When you is essentially a queue, but rather than just queuing up, just lining up before the counter and waiting for the services, okay? Like a wheel queue, you also have a priority. So when you are adding a new data item to a priority queue, you also give a priority store to it. Okay? So I understand that some students, you may not learn priority queue in the data structure course, okay? But you can imagine a priority queue similar to the ER of the hospital, in the emergency room of the hospital, okay? The patient will not be treated just based on their arrival time.
It's the emergency.
Yes. So the hospital doctors will prioritize the patient according to their risk factor. If a patient is from a car accident, you know that and he has a major trauma, okay, a major injury with a very big wound, okay. I don't want to make the lesson too scary, okay. You understand what I say, okay? In a major car accident, the patient is in critical ill condition, okay. Then of course that patient will be assigned with a higher priority, okay. And if a patient is just having a common cold, then that patient will be assigned with a lower priority, okay. And the doctors are treating the patient according to their priority score. Okay, so this is how the ER in the clinic and in the hospital work, right? So this is how priority queue works. Okay, when we are trying to assign to record the data items, we also add a priority score to the item. Yeah.
Okay, so I'm just trying to check my understanding. Like the priority queue, just simply means that we treat them by the priority. So we can treat them either by the from the highest risk factor to the lowest risk factor.
Yeah.
But in the uniform cause search, we only prioritize the cheapest ones.
Yeah. Yes.
Right.
So at the end of the day, priority queue is you just when you are inserting the data item, you also give a number that indicates the priority. Okay, the priority can, if you are using the priority queue in the hospital, then it will be the risk factor of the patient. If the priority is used in the uniform cause search, then it will be the past cause of the dog. Okay, okay. And I understand that you haven't explicitly learned the concept of priority queue in data structure course, right? But I know that you must have learned one thing. Heap. You must have heard of a 3 data structure called a heap, right? The heap have one property. That is the highest number or the lowest number will be the root node. Okay. And if you haven't learned data structure, that's all right. Okay. I'm just trying to recall the memory of the student who has taken the data structure. Okay, so essentially, the heap is the one of the most simplest implementation of the priority queue is just use a heap as the priority queue. Okay, okay. But for a student who don't know heap, okay, you just remember one thing. You just will always remember one thing. We are not computer science students. So we don't need to implement everything from scratch. Okay? 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 I understand that many of you are extremely interested in programming and you always want to implement things from scratch. But in reality, when we are working with computer softwares, even for computer science students, we don't implement things from scratch. Okay? So you only need for this course, you only need to understand that in this world there is a thing called priority queue. And when you're working in priority queue, when you add an item to a priority queue, you add the item with a priority score. Okay. And when you retrieve an item from the priority queue, the lowest priority will get it depends, okay? It depends how you define priority, okay? If you define the lower value to have a higher priority, then the lower value priority values item will get selected. Okay? And if you define the priority value could be higher to a high priority, then the item with a higher priority value will get selected. Okay? So in other words, okay, essentially, you can consider priority queue as a data structure. When you add item to that data structure, you also tag along the priority value. Okay, and when you retrieve an item from the priority queue, the higher the higher priority the item will get selected first. Okay, okay, and the definition of high priority depends on your actual problem. So sometimes you may consider the lower value to have a higher priority, and sometimes you may consider a high value to have a higher priority. Okay, it depends on your applications. Okay, okay, and because we are not computer science student, we are not computer science student, we don't need to implement everything from scratch. Okay, so in fact, when you are working with Python, you can actually use a library called a heap queue to help you implement a priority queue. Okay, so you don't need to know how to implement a priority queue, you just need to know how to use it. Okay, okay, okay. And you also notice one thing, like heap queue. Why is called heap queue? Because underlying a priority queue, the simplest implementation is just use a heap tree as the queue. Okay. One of the properties of the heap tree is that the root node will always be the highest number or the lowest number among all the numbers stored in the tree. And using these properties, we can actually adapt the heap as a priority queue. Okay, but this is just supplementary information for the students who learn their structure. For others who don't learn their structure, you just need to remember one thing is that in Python we have a library called heapqueue that allow us to implement a priority queue. Okay, and that's it. That is good enough for our course. Okay? Okay, and you also need to know the underlying principles of priority queue, and that will be good enough. Okay? And here is the examples on how the heap queue in Python really works. Okay? We still need to create a list. Okay? As you can see here, we created a empty list called the queue. But when we interact with this list, we will use the functions provided by the heap queue library to interact with the list we created. Okay, that is the heap queue library contains the source code that can adapt a list into a priority queue. Okay, so when you are trying to use the heap queue library, what you do is you first create a list, and then you let the heap queue, heap push, and heap queue, heap pop to handle the list. Okay, if you don't interact, if you don't handle the list, and you keep on using the heap queue, heap push, and heap queue, heap pop to manipulate that list, then you successfully convert this list into a priority queue. Okay, that is to make things simple. You can consider Python have implemented some source code that will convert a list into a priority queue.
Just don't think about, just don't overthink, just
Yes,
plug it in.
yes.
That's it.
Yes. Okay. And to use this library, you just create a list. Okay. And then you interact with the list using the heap push and heap pop. Okay. Kaspersky is being very helpful, over helpful in protecting my computer. Okay. So as you can see here, this is how you this is how you create a priority queue in your source code, in your Python program. Okay? Okay. So any questions? And when you are heap hop is easy, okay? You just consider heap hop as I take the highest priority item from the priority queue. But for heap push, we need to explain why. We need to explain how we manipulate the heap push, or how we use the heap push. Okay, you can see in the heap push we have two different arguments. The first argument is the list that store the priority queue. Okay, and the second argument. It is a tuple. You can consider this tuple as a stationary list that contains two items. Okay, the first value is the priority, and the second value is the element you want to put in the priority queue. Okay, okay, and in this implementation, you will see that lower value means a higher priority. Okay, this library default lower priority value means higher priority. Okay, okay. It takes lower value as higher priority. Okay, okay. And you may think it's a professor. So how I can implement a system with high value become high priority? I just add negative value to it. That's it. Okay, okay. So you may ask is, professor, so I have a system that takes lower priority value as higher priority. So how, if I want to convert this priority queue into a queue that high value means higher priority, how I do it? You just add a negative sign to your priority value, then the priority queue becomes a queue that takes higher value as higher priority.
So in this case, how would you do it? Like, how would you add it?
So I have a priority value, right? And I have priority value, right? Before, for example, I have a priority value of 5. I will add a negative to the priority value, and it becomes -5. And when I add the item to the priority queue, I will add negative pi as the priority. Okay?
So in the code, how would you add the
I just add the negative sign. That's
No, I mean the priority, because the priority is not explicitly written in the left hand side. You know what I mean?
it is written right here. Okay, this is the priority, this is the element. So when you add the
Okay.
element into the queue, you can actually change how the priority value is also being added as well. So at that moment, you add a negative, then this system will consider higher priority value as higher priority. Okay? Okay? So any questions? So any questions? So any questions? Any questions? Any questions? And this is how the HipQ library is being used in Python coding. Okay? Okay? And as you can see here, this is the implementation of the uniform call search. And if you take a look on the source code here, you can actually see that the fringe is being replaced with the HipQ library operations. Okay. So I believe that it is better we all just open up the source code. Okay. So wait, I wanted to what this is the buffer search and where is the uniform call search? Okay. So at the left we have the buffer search, and at the right we have the uniform call search. And and now in the computer screen, I actually put the buffer search and the uniform call search side by side. You can actually see the main differences that we have is the fringe. At the left, we are using the queue, and at the right, we are using a priority queue. Okay, and because we are using the heap queue as the library for implementing the priority queue, so you can see I will use the heap push and the heap pop. The heap push and the heap pop, yeah. The heap push and the heap pop to manipulate the fringe. Okay, so you can see here, this is the heap. The pop of the queue is replaced by the heap pop of the priority queue, and the append, okay, that is the enqueue operation of the queue is replaced by the heap push function of the priority queue. Okay. Okay. So you can actually see these two algorithms is the major difference is that we only swap out the fringe being used. Okay. Okay. And let's take a look on the priority queue operation for the heap for the pop. Okay. For the queue, okay, it is very easy. Okay, you just take a value from the priority queue. That is no major discussion. Okay. But for the enqueue, for the heap push, okay, let's take a look at what we written there. Okay. The first value is the PQ. Okay. We need to specify the data structure, the list for storing the information of the priority queue. So there's nothing to discuss. And for the second argument, this second argument is actually the value we are going to add to the priority queue. Okay, and you can see that this is a tuple of two values. Okay, that is we are adding a pair of values to the priority queue. And if we take a look on this pair of values, the first value is the priority, and the second value is the actual item, as the actual search node we add to the priority queue. Okay. Maybe I will maybe now I will enlarge it, see if I can and make it bigger. Okay, it's better. Okay. Okay. And the first item is the priority. Okay, so the first value in this in this pair value is the priority value, and the second value of this pair value is the search node we added to the priority queue. Okay, to the fridge. Okay, and if you take a look on the value we use as the priority, you will see that we are using the path cost of the search node as the priority. Okay, okay, that is in the uniform call search, we are essentially choosing a node that have the shortest distance from the root node, and then we explore that first. Okay, 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 and one concept that you need to know is that in this selection process, we are essentially using the information that we have right now, and then we make the decisions. Okay, we make a very simple decision, and that is called a greedy search. This is also considered as a so-called greedy search. Okay, okay. Essentially, when you are performing a search with the information that you are having right now, and you do a very quick decision, then you can call this as a greedy search, okay, or greedy algorithms. Okay, okay, okay. You in the future you may have heard a term called greedy algorithms or greedy search. Okay, that when you heard a term called greedy search or greedy algorithm, it actually means that you do not take the full picture and you only take partial information, and then you already make the decision. That is called greedy algorithm or greedy search. Okay, greedy search. The word greedy doesn't really mean that you want to earn a lot of money, that kind of greedy. Okay, greedy means you try to make a decision before having all the information. Okay, then that will be called a greedy algorithm. Okay, and here we have an example. Okay, so we are using the same example that we have in the past. I understand that after the Chinese New Year holiday, you already don't understand, you already forgot about this slide. So I will explain again. Essentially, in this slide, at the left-hand side, we have this area for the search tree. And at the right-hand side, we have the search space. And at the bottom right-hand side, we have the priority queue. Okay. And the search space, the state diagram is actually a simplified version because we want to make our discussion simpler. Okay. And one thing you need to remember is that the arrows, the arrowhead, okay, the triangle pointing, the triangle pointer right at the end of the edge, okay, those are representing the direction of the transitions. Okay, if for example, if you take a look on Cebu and Remedial Reacher, okay, we have an arrow pointing from Cebu to Remedial Reacher. That means that the agent can transit from Cebu to Remedial Reacher. Okay, and backwards is not allowed because we don't see an arrow from Remedial Reacher to Cebu. Okay, okay, okay. So this is something you need to remember. This is something you need to remember. This is a common notation. If you see a network in computer science and data science. And when you see arrowhead within the edges of the network, the arrowhead is representing the directions of the connectivities. Okay? Okay? That is when you see arrow from Cebu to Remedial WeChat, that means that the agent can go from Cebu to Remedial WeChat, but backwards is not allowed because we cannot see arrow pointing from Remedial WeChat back to Cebu. Okay?
Just like the logic symbol. So
Yeah.
yeah.
But you may say is Professor. So in the beginning of the course, you show us a network diagram like this. There is no arrowhead. So how I understand this graph? Easy. If you say graph doesn't have arrowhead, it actually means both ways. Okay? If there is no arrowhead, it actually means both ways is allowed. Okay? 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 This is in fact a common notation of graph or network in computer science and data science. Okay? You may take a look on it because in the future, when you need to learn about graph or network, okay, you will come across this notation again. Okay? Okay. And now we start from Cebu, okay? And from Cebu, in this network, we see that the Cebu have two arrows pointing to Pythagoras and Remedial WeChat. So we add Pythagoras and Remedial WeChat to the search tree. Okay, we first expand Cebu because Cebu is the root node, and after expansion, we add the Pythagoras and Remedial WeChat to the search tree because Cebu have two arrows pointing to Remedial WeChat and Pythagoras. Okay, and because the Cebu to Pythagoras is 99, so when we add the Pythagoras to the priority queue, we use 99 as the priority. Okay, and for Remedial WeChat, the Cebu to go to Remedial WeChat take 80 path cost. So the Remedial WeChat will be added to the priority queue with a priority of 80. Okay? Okay? And then because the Remedial WeChat have a smaller priority value, that means that it has a higher priority. Okay? In the uniform call search, we prioritize the node that have a smaller path cost. Okay? And because our heap queue actually will prioritize items that have a smaller value of priority. Okay? Okay? That is smaller value means high priority. Okay? So as a result, that is the reason why when we add the nodes into the priority queue, we can just directly use the path cost value as the priority. Okay? Because the heap queue implementation will actually select the items with lower priority value first. Okay? And as a result, and we want that for the uniform call search. So as a result, we just add the nodes with the path cost into the priority queue and we can call it that. Okay? And because Remedial WeChat have a path cost of 80, and under our heap queue design, the Remedial WeChat will get selected and explore first. Okay? Okay? So as a result, the Remedial WeChat get expanded. Okay? And when Remedial WeChat get expanded, we refer back to the state diagram, and in the state diagram, we see that the mutual reacher is pointing towards Kevlara and also Pithesti, okay? I know that my pronunciation here is bad, okay? But you understand what I'm saying, okay? So in the state diagram here, you see that the mutual reacher is having two arrows pointing to Kevlara and also Pithesti. Okay, so we add the Pithesti and the Kevlara into the search tree. And in this search tree, we know that for SIBO to go to Pithesti, it need to take the cost of the 80 plus 97. Okay, the path cost of Pithesti is the path cost of the mutual reacher plus the step cost going from the mutual reacher to Pithesti. Okay, so it will be 80 plus 97. So the value will be 177. Okay, 177 will be the path cost of the Pithesti. So as you can see here in the priority queue, the Pithesti will be added with a priority of 177. Okay? Okay. One issue, one common mistake that I notice students having when they are learning the uniform cost search is that they take the step cost as the path cost. Okay, but step cost only represents the cost needed to go from the parent node to the node that you are having right now. But when we are talking about path cost, we are talking about the cost going from the root node to the node you are having right now. Okay, so the path cost of the Pithesti should not be 97, should not be 97. It should be 80 plus 97 because the path cost of the mutual reacher is 80 and the step cost of mutual reacher to Pithesti is 97. So the path cost of the Pithesti is 97 plus 80. Okay, you should consider the path cost as the sum of the step cost going from the root node to the node that you are working on right now. Okay? Okay? Okay. So any questions? So any questions? Any questions? And using this principle of the path cost, we know the path cost of the Pithesti is 177. And that is why in the priority queue, we will add the Pithesti with a priority of 177. Okay? Okay? You need to go and wash your faces. It seems to be very tired. So we also add the Kevlara under the same principles. Okay? 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 Any questions? Any questions? Any questions? So this is how we operate the uniform cost search. Okay, it is not that difficult. Okay? You just need to remember we are actually choosing the node of exploration according to the path cost. Okay? Okay? And also, I actually discussed this in the previous lectures. Okay? When we are talking about search tree, a node in the search tree is not just a node. A node in the search tree is also representing a path from the root node to the node we are talking about right now. Okay? So for example, when we are working with this Pithesti node, the Pithesti node shown here that my mouse pointer is pointing at right here. It is not just one node in the search tree. it is also a representation of a pathway from the root node to the state that this node is representing. Okay? In the search tree, we can from the search tree, okay, we can deduce the path from the root node to any node in the search tree, right? So, for example, if we are at the p-test now, we can do a backtrack from the p-test back to the Cebu to root node, and then we get the path, and then we flip it backwards. Then it becomes the path from Cebu to p-test, right? Right? So in fact, each node in the search tree is recording a pathway from the root node to the node in the search tree. Okay? Okay? In this search tree, the p-test node is not just a node in the search tree. The p-test node also is representing a potential pathway from Cebu to p-test. Okay? Okay? And the pathway will be Cebu to Remedial WeChat to p-test. Okay? Okay? You must have this understanding, okay? This in the search tree, each node, every node is actually representing a path from the root node to the node we are working on. Okay? The Cavera node is representing a path from Cebu to Remedial WeChat to Cavera. Okay? 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 So when we are prioritizing the node for exploration with the path cost, we are actually prioritizing the pathway for exploration as well. Okay? You can actually take the uniform core search in this perspective as well. Okay? One thing you need to always remember about the search tree is that the search tree is a data structure that keeps track on the path that we have been exploring so far. The p-test node is actually representing a path from Cebu to Remedial WeChat to p-test. Okay? Okay? The pathway is being encoded into the search tree. Okay? You can consider the search tree as a collection of pathways starting from the root node. Okay? 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 So when you are choosing a node for exploration in the search tree according to the path course, you are essentially selecting the path for exploration as well. You are choosing the shortest path from the root node right now for further exploration. Okay? And each time, and in the uniform core search, you keep on taking the shortest path from the root node for exploration. Okay? Okay? So at a moment when you first reaches the goal state, that pathway will be the shortest pathway from the root node to the goal to the goal state. Okay, do you see what I'm referring right here? In the search tree, each node is actually representing a pathway, not just a state in the search space. Okay? For example, the p-test node in this search tree is representing a pathway from Cebu to Remedial WeChat to p-test. Okay? Each node in the search tree is representing a pathway. Okay? And the path cost of each node in the search tree is representing the path cost that the path is represented by that node. Okay? The path cost of the p-test node is actually the path cost of Cebu to Remedial WeChat to p-test. Okay? Okay? So In fact, each time when we are going to the priority queue and we are selecting the node with the smallest path cost for exploration, we are in fact selecting the shortest path from the root node for exploration. And when we are doing the uniform call search, each time we are selecting the shortest path that is remain unexplored and re-exploring. Okay. So in the uniform call search, in each iteration, we are selecting the shortest distance pathways from the root node for exploration. Okay. Any question on that? Any questions? Do you understand what I'm trying to say? Okay. So let's consider this. Now the uniform call search reached the goal state for the first time. Okay. According to our operation, the pathway we are exploring is always the shortest pathways from the root node right now that is unexplored, right? The moment we first reaches the goal state, the pathway from the root node to the goal state will be the shortest. Okay? Because we keep on only checking the smallest path when we are doing exploration. We keep these properties, right? We keep these properties in the iteration by using the fridge, by using the priority queue. Okay? So that is why the uniform call search can always find the shortest path from the root node to the goal state. Okay? From the initial state to the goal state, it can always find the shortest path, and that's the reason why. Okay? Of course, if there is a rigid mathematical proof that actually demonstrates the uniform call search is optimal. Yes, there is a mathematical proof for it, okay? But if too involved, then I will not go for it in this course. Okay? But you can kind of able to understand why uniform call search can always give you the best path, the shortest path. Because in each search, in each time when you explore a path, you take the shortest one for exploration. And you will stop the moment you first find the goal state. Okay? So the moment you reach the goal state also you are having the shortest path from the root node to the goal state. Okay? So any questions? Any questions? Do you think that is easy enough to understand? Do you think that is easy enough to follow? Okay. The main principle you need to understand the uniform call search is that each time we explore the nodes with the smallest path cost. And the node itself, not just a node in the search tree. You must remember the node in the search tree is representing a pathway. The p-test here not just represent p-test, it's representing a route from Cebu to Remedial WeChat to p-test. It's representing a route. It's representing a path. So we choose node with the smallest path cost for exploration. We are actually selecting the shortest path in the search tree for exploration. Okay, and the moment we reach the goal state, that means that we are also holding in our hands the shortest pathways to the goal state, because we always explore the shortest path in our search algorithm. Okay. So the moment we reach the goal state, that path will also be the shortest path from the root node to the goal state. Okay? 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 But this approach actually has an assumption. Okay? The assumption is that the path cost will always increase when you go one more step. Okay? 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 If you have an edge that is smaller than 0,
that will be backward.
yes. So uniform cost search only works if all the edges have positive path cost or step cost. If you have negative step cost, then if you have a loop, then it will keep on reducing, right? So that is the reason why when you talk about uniform cost search, all the step cost must be larger than 0 for the uniform cost search to work. And that's the reason why. If you have one step cost that is more than 0, that means that you created a loophole for this approach. Because in the uniform cost search, we pick the smallest value, path cost value node for exploration. If there is an edge that is negative, that means that going through the edge will always reduce the path cost. Okay? So we will actually go in, and also let's consider a situation that the state diagram have a loop. Okay? Okay. And if that edge is negative, that means that going through that loop always reduce the path cost. That means that the algorithm will stuck it at that loop and it cannot escape. Okay? Okay. And that is the reason why uniform cost search is only optimal when your step cost is larger than 0. Okay? Because it works on a premise that each time when you make one step forward, when the agent make one step forward, the step cost, there will be a positive step cost and the overall path cost will increase. Okay? The uniform cost search is actually based on that premise. Okay? And you must remember. Okay? And as you can see here, when we go to OpenPTest and we explore, and next time we explore the Fagros, okay? Because the Fagros is 99 versus the p-test and Cavera, okay? And in the Fagros, it will go. The Fagros have one arrow pointing to Bucharest. So the value of the Bucharest is 211 plus 99, because Cebu to Fagros will be 99 and Fagros to Bucharest will be 211. So adding up together will be 310. So Bucharest will be 310 here, okay? But p-test is having a smaller path cost than the Bucharest node right here. So we'll explore the p-test first. Okay? And when we take a look on the p-test, the p-test have an arrow pointing to Cavera and the arrow pointing to Bucharest. So we will also add Bucharest under the p-test and add Cavera under the p-test. Okay? And one thing I hope you observe right here. Notice in this search tree, we have 2 Bucharest, right? But these 2 Bucharest nodes are different because these 2 nodes are actually representing two different pathways, okay? The Bucharest right here is representing a pathway from Cebu to Fagros and to Bucharest, okay? And the Bucharest here is and the Brookers at the bottom is representing a pathway from Cebu to Remedial Richa to Bethesda and to Bucharest. Okay? So here's one thing you must remember. In the search tree, a node not only represent the states that it represents, it actually is encoding a path as well. Okay? Okay? And as you can see here, among all the path we have here, we have the Kevlar node, we have the Bucharest node, we have the Kevlar node here again, and we have the Bucharest node. Okay, and the Kevlar from the Cebu to Remedial Richa to Kevlar have the smallest path course, but it is pointing nowhere. Kevlar just doesn't have any node that it can go to. So we just remove Kevlar from the RSQ and we don't add node here. Okay? Because in the state diagram, you can see the Kevlar is pointing nowhere. Okay? It's going nowhere. Okay? There is no arrow pointing from Kevlar to other nodes. Okay? So if the agent is actually reaches the Kevlar, there is nowhere it can go to. Okay? So when we dequeue the Kevlar, we don't add any new node to the priority queue. And that's the reason why. Because the agent can go nowhere else if it is at the Kevlar. Okay? Okay? Then we take a look on Bucharest because according to our priority queue, the Bucharest have the smallest path course right now. Okay, and because the Bucharest is our goal state, so we can stop. Okay, okay, and also one thing we must be remembered is that when we take node for exploration, we are using the priority queue, and the priority queue will always point us to the node with the lowest path course. Okay, so the Bucharest we are exploring right here is the shortest pathways. Okay, is the shortest pathways. Okay, okay, and as a result, the uniform call search is actually able to search the shortest pathways from the initial state to the goal state. Okay, okay. In fact, some students may be interested in a proof. Okay, and one thing you can actually take a look is you can go to the internet and search for uniform call search proof, or you can actually go to search a algorithm called the Dijkstra's algorithm. Okay, the Dijkstra's algorithm is actually operated in a very similar principles as the uniform call search. Okay, so you can also search Dijkstra's algorithm, and you search the proof, then usually you can find a lot of reference materials. Okay, but the proof of the uniform call search is being optimal is a little bit too involved, so I will not discuss it in this course. Okay, you just need to remember one thing is that the uniform call search it only works when all the step cost is positive value. Okay, okay. If all the step cost is positive values, then the uniform call search is optimal. That means that the uniform call search can only find the shortest path from the initial state to the goal state only when all the step cost is positive value. Okay, this is something you must remember. Okay. And essentially, the uniform call search is the same as the worst case scenario of the uniform call search is the same as the breadth first search. Okay, so you can see the type and the space complexity of the uniform call search is similar to the breadth-first search, okay? And I will not go through the details as we have already go through how to compute the complex time and the space complexity of the breadth-first search. Okay? Okay. And one thing I also want to remind every one of you is that when we are evaluating the performance of the uniform call search or breadth-first search, we are counting the number of nodes that we need to handle. Okay? But in fact, we are taking a lot of assumptions here. Okay? We are assuming the fringe is extremely efficient and it takes almost no cost to get the item to you. Okay? 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 So, but let's consider this. Let's consider this. If your priority queue need to is implemented as simple as you take an element out, you do a sorting on the element before you take an item out, then the time complexity will be different. Okay? Okay. Okay. One thing I need to remember every one of you. One thing I need to remind every one of you. When we are computing the time and the space complexity of the breadth-first search and the uniform call search, we are assuming that taking an item from the queue or from the priority queue only takes around 1 to 2 instructions or a fixed number of instructions for the CPU. Okay? Okay? If your priority queue is implemented so badly that you need to do a sorting, okay, before you can find the shortest priority items, then the time complexity of the uniform call search will not be this figure. Okay? 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 And that is the reason why you learn heap for data structure calls. Using the heap, you can control the time needed to get the shortest number item with O1 complexity. Okay? 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 And that's the reason why it is very common that you use a heap to implement a priority queue. Okay? So any questions? Any questions? Any questions? Any questions? Any questions? And the next thing that we need to talk about is the depth-first search, okay? The depth-first search is again very similar to the breadth-first search, but we replace the queue with the stack. Okay, we replace the queue with the stack. Okay, so stack is very simple. You just add items to the head of the stack, and when you retrieve item from the stack, you are retrieving it from the head of the stack. Okay. So I believe that most of you here already learned what is a stack in your data structure course. So I will not go further with the implementation. Okay. And here in this course, we are using the if you take a look on the coding that I included, you can see that I am actually using the DQ. I'm actually using the DQ data structure in the Python to emulate a stack. Okay. And let's take a look on the Python code. You can see that the this is the at the left is the breadth-first search, at the right is the depth-first search. Okay, you can see that the main differences is of the depth-first search and the breadth-first search and the depth-first search is only one line. Okay. For the breadth-first search, I am using queue.append. So when I'm adding new items to the DQ, I'm adding it at the right-hand side. But for the breadth-first search, for the depth-first search, okay, for the depth-first search, I am taking out item from the left-hand side. Okay? For both algorithm, I am adding new items to the fringe and the left-hand side. But for the buffer search, okay, look, sorry. I was saying this manner, okay? For both the buffer search and the depth search, I am getting items from the left-hand side of the DQ. But the major differences of the buffer search and the depth search implementation is that for the buffer search, I am adding new items to the right-hand side of the queue. So it is a first in, first out there. And for the depth search, I'm adding items to the left. So it is a last in, first out there structure. Okay? Okay. The differences between buffer search and depth search is smaller than you believe to be. Okay, just one line of code and that's it. Just one line of code, then that will make the difference from the buffer search and the depth search. Okay, you can compare it side by side, and you will find that they both are they are really very similar to each other. The major difference is that at the left-hand side, I add items to the right-hand side of the DQ. And for the depth search, I'm adding items to the left-hand side of the DQ. So that is the major difference here. Okay, and that difference will be enough to change the buffer search into depth search. Okay. Okay. Any questions? Any questions? Any questions? Can every one of you follow what he up to now? Any questions? And let's go for a dry run. You can actually we will start from Cebu, okay? And from Cebu we'll go to fragrance and remedial region. So we add it to the stack, okay? And because the fragrance is in the stack first, so we'll explore the fragrance. And when we explore the fragrance will go to Bucharest. So we add the Bucharest into the stack. But notice that we are adding it to the head of the stack, okay? So next time when we need to choose a node for exploration, we choose the Bucharest over the remedial region, okay? Because the Bucharest is appearing later, so it will process first. So it will get processed first, okay? So as a result, we export the Bucharest, and as a result, we will stop the search because we already reached the terminal node, the goal state. Okay, so that is so-called the depth search. Okay, so any questions? And if you go to the internet and search and go to internet and try to find references information related to depth search, you may find that people don't implement depth search in this manner. Instead, they implement it using recursion. But you may ask this, Professor, in the recursion, I don't see any fringe, I don't see any queue. So how I can implement depth search with recursion? And if we want to talk about the concept of the of recursion implementation of the depth search, we need to figure out one thing: how functions is being executed. Okay, you should have learned in your programming course that program is just like a subprogram. A function is just like a subprogram, and you can call the subprogram, and it will execute and then perform some tasks. Okay, and you can also give some arguments to the function as well. Okay, and when you are calling a function call, the calling program will suspend execution, the caller of the function will suspend execution, and the function being called will get executed. And after the function being called get executed, it will return back to the caller, and the caller will keep on execution. Okay? And let's take a look on this example. In this example, you can see we have a function called fun1, right? And we have another function called the fun2. And the fun2 is calling fun1 is calling fun2, okay? And at the end, we are calling fun1. Okay? Okay. So based on your understanding of program, you know that the fun1 here and the fun2 here are definitions, right? Are function definitions, right? And we see a fun1 coding here, emotion here. So the fun1 being invoked and the fun1 will get executed. Okay? And when the fun1 get executed, it will execute the print statement here first. Okay? And when we see the fun2, the fun1 will suspend execution and the fun2 will get executed. Okay? And after the fun2 execute these two print statements, then it will return to fun1 and the fun1 will finish the rest of the execution. Okay? Okay. So let me ask you a question. Have you noticed the order of execution? The order of execution is last in, first out, or first in, first out. Fun2 being called later, but fun2 finish execution first. Right? Right? So based on your understanding of program, you will notice something about fun2 get called the latest, but fun2 get finish execution earliest. Right? 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 So let's think on let's consider how function call works. I call function 1, and the function 1 first print statement is executed, and then I call, and then fun2 is being called, the fun1 gets suspended, and I run fun2. And the fun2, I will run these two execution print statement. And after the fun2 finish execution, I can finish fun1 execution. Okay? So we notice one thing, right? Fun2 being called the last, but it can finish its execution the earliest. Right? 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 So it's some sort like last in, first out, right? Makes sense, right? And you may ask is how computers actually implement, how computer behind the hood is able to manage the function called execution in this manner. In fact, in the computer, we have a thing called the call stack. Okay? When you are calling a function, the execution information, just as the variables of the function, will get stored in a data structure called the call stack. Okay? And the call stack is actually, and the last in first out properties of the stack is actually making the function being executed in this manner. Okay? Okay. Okay. And that is behind the hood why you can use recursion to implement a depth search. Essentially, you are using the call stack as the stack to give you the last in, first out ordering execution such that your depth search can perform. Okay? The ultimate thing that you need to have to run a depth search is simple. You just need to make sure the nodes are explored in the last in first out order. Okay, depth search is simple. As long as you can explore the nodes in the search tree in the last in first out manner, then the depth search can be performed, right? So there is a concept the concept can manage the function order and the function because the order of the function execution is managed by the stack. It is the last in first out ordering. Okay, so if we use recursion, if we use the function ordering to our advantage, then we can use recursion to implement the depth search. Okay, and that's the reason why you will see many implementation of the depth search will use recursion. Behind the hood, it is making use of the last in first out ordering execution of the function call to control what node being explored first. Okay. So any questions? So if you do not have any question, then this is the end of today's lecture. Okay, we will need to stop 10 minutes before the scheduled time, and I will end the recording here as well.